Chapter 3, Part 3, Patterns in Organic Chemistry. Now, in this last part of Chapter 3, we're going to be leaving the concept of acids and bases just a little bit and focusing on the different patterns that you often see in organic reaction mechanisms. So if you can recognize the patterns, you can solve pretty much any problem. And the way that I usually describe this to my students is that it's kind of like a dance. When you're first learning dance, you learn individual motions and steps. You learn how to do a pirouette, you learn how to do a jeté, pas de bourrée. You learn all these different things, and then you put them together in many different ways so that you can create very different pieces of choreography. Patterns in organic chemistry are very similar. You have 5 basic things that can happen. You have protonation and deprotonation, which are just opposites of each other. You have the nucleophilic attack of an electrophile. You have bond rearrangement and bond breakage. These are the only 5 possible things that can happen, but they get rearranged in a bunch of different ways. And so if you can recognize the patterns and recognize the possibilities, then it kind of limits what you can do, and organic chemistry won't seem as big and confusing if you can kind of narrow down your options. Our first pattern is protonation. So in the reaction of ethanol with hydrochloric acid, the ethanol has lone pairs on the oxygen, and it's going to pick up a proton from hydrochloric acid. When it forms a bond between the oxygen and the hydrogen, which is what this arrow is demonstrating, that also causes the bond between hydrogen and chlorine to break, which gives us a protonated form of the ethanol and the chloride anion. And I want you to notice also that there are 2 different ways of looking at this. You can say that the ethanol was protonated, or you could say that the hydrochloric acid was deprotonated. These 2 things are just opposites of each other. When one occurs, the other occurs as well. You can also look at this with alkenes. Alkenes are capable of picking up protons as well. So the pi electrons in that double bond can pick up a proton from hydronium. And so now one of these hydrogens is the hydrogen from hydronium. And the other carbon here ends up with a carbocation. And I want to explain why for a second. We took the electrons that were creating a double bond between these 2 carbons, and we used them to make a new bond between carbon and a hydrogen. So those electrons are still attached to this carbon, and the other carbon is now missing electrons, which is why it now has a positive charge. And this also gives you water as a conjugate base. And so this is something really common that you're going to see pretty quickly in organic chemistry. Now, the species that we formed here is called a carbocation. This is a carbon that is missing 1 bond, missing 1 electron pair, and is therefore positively charged. Okay, let's look at deprotonation. And again, this is just the opposite of protonation. Protonation and deprotonation occur rapidly at equilibrium. The moving around of a proton is the fastest reaction in organic chemistry because protons are tiny. There's nothing getting in the way of it being attached to something else, and it's constantly at equilibrium. So let's look at the reaction of ammonium and acetate. Ammonium has a positive charge. It has an extra proton here. And acetate has a negative charge. It's looking for a proton. So it can pick up one of the protons on ammonium, and then the electrons in this covalent bond get put back onto the nitrogen. This leaves us with ammonia, which has a lone pair on the nitrogen, and the conjugate acid of acetate, which is acetic acid. Our next pattern is the nucleophilic attack of an electrophile. before we can look at this, we have to go over some vocabulary here. Electrophile literally means electron loving or seeking. This is something that is either positively charged or has a partial positive charge. It is going to be a Lewis acid, and good examples of this are carbocations, acidic protons, and carbonyl carbons. A nucleophile is nucleus loving or seeking. It is going to have a negative charge or lone pairs or pi bonds. It's going to be a Lewis base. It is looking to attack a positive center, and it includes things like alkoxide anions, carbanions, amines, water, the hydride anion, and this list could go on. The other important thing to know about nucleophiles is that we often use this word attack, which sounds kind of weird, but a nucleophile is going to be a place that has a high density of electrons. So a reaction arrow always starts at a nucleophile. And so if the nucleophile is going, or if the electrons are going from the nucleophile to the electrophile, the terminology is that the nucleophile is attacking the electrophile. So let's look at some examples. In this first example, we have boron trifluoride and ammonia. This is kind of an interesting one because this is really a Lewis acid, Lewis base interaction, which all nucleophilic attacks are. The boron is going to have a partial positive on it because of the dipoles pulling electron density away from the boron and creating partial negatives on all of the fluorines. So the nitrogen on ammonia is going to be very interested in that boron. And what you end up with is this kind of weird complex where the boron and the nitrogen are bonded together. And now you have the fluorines all attached to the boron. Boron was neutral, and now it has more electrons on it than it wanted, so it has a negative charge. And nitrogen used to have full ownership of that lone pair that is making this covalent bond, but now it has to share it, so it's actually lacking electrons and becomes positive. So we've created a complex between the two compounds. Now, one that is a little less complex is the one below it. You have the chloride anion and a generic carbocation. I just used some R groups here to represent other carbons. This one's really easy to tell what's going to happen because opposites attract. The negative charge is going to attack the positive charge, and you're going to end up with chlorine attached to that carbon. All four of those alkyl groups still on there, and chlorine still has 3 of its lone pairs. The other lone pair has been used to make this bond, and so chlorine lost a little electron density, which is why it's no longer negative, and carbon, which was positive, gained some electron density, and now it's neutral. One more example. In the one below, we have a ketone, which has a dipole, so there's a partial positive on this carbon and a partial negative on the oxygen. Another way of looking at this is through the resonance form. Where you have negative charges on the oxygens and a positive charge on the carbon. Here, this is just like before. It's really plain to see that the hydrogen is going to want to attack that carbon. And it wants to attack it, even as it's a partial positive, but it's really clear in the resonance form. And so when hydride attacks a ketone, you end up with an alkoxide, a negative charge on oxygen and another hydrogen on what used to be the carbonyl carbon. Now, this next pattern is one of the more difficult ones to understand. This is bond rearrangement. Now, bond rearrangements can occur when you create kind of an unstable intermediate of sorts, and there's a possibility where you could rearrange to make something that is more stable. So, for example, we have two different examples of carbocations. In the first example, we have a carbocation on a secondary carbon. So notice this carbon has 2 other carbons attached to it, so it is secondary. And we don't know this yet. We will get to this a lot later, but carbocations are more stable when they have more carbons on them. So one of the things that is possible is that if you have a hydrogen atom on a highly substituted carbon next door, this carbon has 1, 2, 3 carbons attached to it, so it is tertiary, then that hydride can actually just slide over here. And so you end up with 2 hydrogens on that original carbon. Let's go ahead and just label these carbon A and B. And then you have a carbocation on carbon B. So carbon B lost its hydride and the electrons that go with it, and they moved over to carbon A. And this is called a hydride shift. And it's important to note that what we're moving here is hydride, which is different from a proton. Hydride has 2 electrons and a negative charge, while a proton has no electrons and has a positive charge. So protons are associated with acids, hydrides are bases. And there's one other possibility. If you look down at the next example, notice that on the neighboring carbon, which is very highly substituted, it has 1, 2, 3, 4 things on it. It is a quaternary carbon. We don't have any hydrogens to move, but we can take an entire alkyl group and slide it over, just 1 carbon. And so if we're using the same labeling of A and B, B is now our carbocation. And the reason that we would do this is because our carbocation went from being secondary to tertiary. And the same thing happened in the earlier example. We had a secondary carbocation, which we turned into a tertiary carbocation. And when you do this, it is called a methyl shift. You might also hear it called alkyl shift because you can also move things other than methyl groups. Okay, the last pattern that we have to talk about is bond breakage. And this is essentially the spontaneous breakage of a bond to create reaction intermediates. So if you have a highly substituted carbon and a substituent on it that could leave and be stable on its own or be stabilized in the reaction conditions, then that intermediate piece could leave on its own. So for example, here we have T-butyl bromide. Bromide is perfectly stable on its own, so it is perfectly capable of just leaving the carbon skeleton behind, which would be those 4 carbons, and leaving a carbocation and being bromide. Now, this is especially possible if you're in a solvent that has something that the ion can interact with, so some ion dipole interactions. The next one has an epoxide, which has been protonated. So an epoxide is a 3-membered cyclic ether. And this is another example where the ring can spontaneously break open to give electrons to something that needs them. That oxygen is very electronegative. It is currently very upset about being positively charged. So we can have it leave with its proton and take the 2 electrons from that covalent bond, and that leaves behind the carbon it was attached to as a carbocation. So this is bond breakage. And this is usually just a reaction mechanism step. It's not going to lead necessarily to the product. Carbocations are not very stable, so this is not a product, and this is not a product either.